Hello friends, this is lecture number 14 of complex analysis. Today we are going to discuss about Cauchy's integral formula, mathematical physics. And before we start this Cauchy's integral formula, this is the previous lectures. Okay, links are given in the description box. So to understand this, you must know Cauchy's integral theorem before you before you watch the video on Cauchy's integral formula. You must know that what is Cauchy's integral theorem. Okay, so that's why I would like to suggest that please watch the previous lectures, okay, first, and then come to this video. Links are given in the description box. And also let me tell you one more thing, that if you want to follow me on Insta, this is my Insta ID, Lakhyajit 123. Okay, so before we start, please subscribe the channel, hit the bell icon so that you get notified when new video will be uploaded, and please hit the thumbs up button if you like my videos, and also share with your friends. Help me to grow my channel, inspire me to create new contents for you. Okay, so now let's start. So here is the Cauchy's integral formula, that if we have a function f of z where z is a complex variable, if this is analytic, this function is analytic within and on a closed curve. There is a closed curve. Suppose if this function is analytic within this curve and on the points, at the points on the curve also, here at the points on the curve also, if this function is analytic on the curve and inside the curve as well, then and if there is a point within this curve, that point is suppose A. Okay, this curve is suppose C, represented by C, and A is a point within the curve A, within the curve C. This A is a point, then within C, then f of A is given by this. So then f of A is given by this formula where z is a complex variable. So hope you have understood this. Now let us prove this theorem. Okay, so now let me clean these things. Okay, so now let us consider a function that is f of z divided by z minus a, which is analytic within a closed curve suppose C, closed curve C, except at z is equal to a, because you see at z is equal to a, this denominator gonna be 0. If the denominator is 0, then this gonna be not defined, right? So that is why this function that we have considered, that f of z is equal f of z divided by z minus a, is not analytic at this point z is equal to a, right? So hope you have understood this. Okay, then z. Now you see here, now let me take the curve C. This is the curve C here. So this is the curve C, suppose closed curve C, and here is a point A, suppose. Okay, here is a point A. Now with the point A, let us draw a circle with the point A as the center, and radius r, small r. Let us draw a small circle, small circle C1, suppose. Okay, a very small circle is drawn, which is suppose C1. This is C1. Okay, this is suppose C1. I have considered this way. C1. Okay, and here you see lying entirely within C. Within C, right? So now this function f of z by z minus a is analytic within the region bounded by C1 and C. Okay, so now you see, so we have considered this C1 very small. Just wait, let me convert this one into simply connected region. So how to do that? Using a cut here. So if you have watched my previous lectures, then you must understand these things. So then this is going to be the direction, and this is going to be the direction. So here you see this inner circle, this one, its center is A, right, and its radius is R. And let me just wait. This inner circle I have drawn here, this one, which is of center A, and its radius is small r, such that this circle C1 is very small, so that r tends to 0, and it includes only this point A, at which this function that we have considered is not analytic, and other than this point, at each and every point, this function is analytic, and those points at which this function is analytic are bounded by these two circles C1 and C. Okay, so that's why if this C1 is such a small circle that it includes, or it encloses only, it encloses only this point A, where this function that we have considered is not analytic, then it must be very small circle such that r tends to 0. R is the radius of the circle C1, right? So we have considered that way. Now let me go to the next slide. Okay, so here you can see okay, this is the two curve that we have taken. This is the two circles we have considered. Okay, so let me go to the previous slide. So here you can see that now this function f of z by z minus a, this is analytic within the region bounded by these two circles, within this region. Okay, so that means the inner circle that C1, this inner circle C1, which encloses A, is so small that this is the only one point A at which this function is not analytic, is enclosed by C1, and it is very small circle such that r tends to 0. Okay, so if C1 is not very small such that r tends to 0, okay, if r doesn't tend to 0, that means if it is not very small, then C1 will enclose more such points at which this function will be analytic. So this function will be analytic not only within these two regions, but also at some points within C1 as well. Okay, so we have considered this here you see, we have considered this inner circle, this C1 is very small such that this f of z is analytic only the region bounded by these two circles. Okay, and there is only one point within C, that is A, where this function is not analytic, not f of z, sorry, not f of z, f of z divided by z minus 1, z minus a. We are talking about this function that we have considered. Okay, so to make this function f of z by z minus a analytic within the region bounded by these two circles, not any other point beyond this C1, beyond this region bounded by C1 and C, this C1 must be very small such that it encloses only this point A where this function is not analytic, right? So hope you have understood these things clearly. So we can say that R, which is the radius of this C1, R tends to 0, right? So here you see that we have already discussed about that Cauchy's theorem in the last video. So please do watch that video for better understanding. So by Cauchy's theorem, Cauchy's integral theorem, for multiple connected region, f of integration f of z by z minus a. So let me write it properly. F of z by z minus a dz c integration on c along c is equal to integration along c1 integration of f of z by z minus a along c1, right, dz. So we have got this theorem that what was the Cauchy's integral theorem for multiply connected region that we have discussed in the last video, that we have considered these two curve C1 and C2, and we have used a cut to make it, to make the multiply connected region to simply connected region, and this is a point A. In that case, we have got this according to that theorem. If there is a function f of z, okay, if there is a function f of z which is analytic within the region bounded by these two, then an integration of f of z along c1 is equal to into dz, integration this is equal to integration of f of z dz along c2. We have used it. We have got that formula. Okay, we have got that theorem. So in the last video, in lecture number 13, so please do watch that video. So now you see here, instead of f of z, we have f of z by z minus a. So using that theorem, we have got this relation, right? So hope you have understood this. Now let me clean these things. Now here you see that integration along c1. Here we can write f of z minus f of a, then again plus f of a, right, z minus a dz. So if you cancel these two, again you're gonna get this, right? So hope you have understood this. So this can be written this way. So integration f of z minus f of a divided by z minus a plus dz then plus integration along c1 f of a by z minus a dz. That's what we can write. So here if you want to write this f of a outside, then you can write, because once you have written f of a, then it's gonna be, it's no longer, so here f of a is not variable. Just wait, let me adjust a little bit. So here you see, you can write this f of a, as soon as you put value here a, then it's gonna give you a constant value. So that's why we can write this one here, right? So let me write it properly. So here we can write this way, okay, 1 by z, integration 1 by z minus a dz, okay, c1. So this is equation number 1, right? So here on the left hand side we have f of z by z minus a c dz. Okay, now let me copy this equation number 1. Let me go to a new slide. Let me copy this equation number 1 and let me go to the new slide. So here you see, this is equation number 1 that we have got. Now what we're going to do here, let us consider that let z minus a is equal to r e to the power I theta, r e to the power I theta. So here z gonna be equal to a plus r e to the power I theta, right? We can consider that way. And if we differentiate with respect to z, okay, if we differentiate it with respect to z, dz by d theta, then what we're gonna have, this a gonna be 0 as it is constant. Then if you differentiate it, then here I gonna comes out here e to the power I theta again, right? That's what we're gonna have. So this implies dz is equal to I r e to the power I theta d theta. Now if we use this result in equation number 1 on the right hand side, first let me evaluate one by one. First let us take this, okay, just wait, let me copy this, just let us take this. So here you see, then it can be written this way, integration along c1 f of z. Here f of z can be replaced by just here you see, let us replace this z by this value of z. Then what we're gonna have, f of, instead of z we're gonna write a plus r e to the power I theta, then minus f of a divided by z minus a. Z is again a plus r e to the power I theta, okay, and then we have a minus a here dz. That's what we're gonna have. So here this gonna be again changed. So here c1 means this is the circle that we have considered of radius r. So here we're gonna integrate it from 0 to 2 pi, right? 2 pi, right? So hope you have understood this. So and this dz gonna be replaced by this I r e to the power I theta d theta, right? So here just wait, now you see, if minus a plus a cancels, then what we're gonna have, then we're gonna get this term only, r e to the power I theta. Then here again r will be cancelled, then what we're gonna have, and e to the power I theta will be also cancelled. Then here let me cut it, then we're gonna get this term only, this is into I d theta. That's what we're gonna have, right? So hope you have understood this. So what are the things that I have cancelled? Hope you have words carefully, right? Just wait, let me do a little bit adjustment here. Okay, so here is the result that we have got after simplification. So as I have already told you that r tends to 0, so that's why this is gonna be 0, right? So if this is gonna be 0, then f of a minus f of a, that's gonna be again 0, right? So here we can write 0 to 2 pi, just wait, 0 to 2 pi 0 to 2 pi f of a minus f of a into within bracket f of a minus f of a I d theta, since r tends to 0, right? We can write that way. So if that is the case, then it's going to be definitely 0, so that's why we have got 0. So we have got this part is equal to 0. Now let us evaluate this one, right? So now let me go to the new slide. Okay, so just let me do it here, just wait. So just wait, let me go clear these things. Okay, now you see here f of a integration along c1 1 by z minus a dz. So if we use these results that we have taken here, then what we're going to have 0 to 2 pi 1 minus, so sorry, here it's going to be f of a, right? F of a, right? So here, and z minus a, here you see z minus a is this r e to the power I theta, right? Then dz will be I r e to the power I theta d theta. That's what we have got. These two are cancelled, this one and this part, these two are cancelled, right? So here we have this I can be taken out, right? So let me write it, r cancel, this one and this one count. So what we can write, we can write I f of a and integration d theta 0 to 2 pi, and if you integrate d theta, then you're gonna get theta, and if you put upper and lower limits, then what you're gonna have, then you're gonna have 2 pi minus 0, that's gonna be 2 pi, right? So what we have, f of a 2 pi, let me write this I here, okay, I. So here we have got integration of f of z minus f of a by z minus a along c1 is equal to 0, and value of this one we have got this, right? So we have got the values of these two. Okay, so using these two values in equation number 1, right? So now this is suppose equation number 2, and let it be suppose 3. So using just let me take a new slide, let me copy this equation number 1. So let me copy the equation number 1, and here is the new slide. So this is equation number 1, and this is equation number 2, equation number 2, and this is 3. So this is nothing but the value of this one, right? C1 f of a 1 by z minus a into dz, means you can write dz by z minus a, this is equal to this, right? So using 2 and equation number 3 in equation number 1, what you're going to have, integration along c f of z minus a dz is equal to, so this becomes 0, right? So 0 plus f of a and this one become this, right? F of a 2 pi I, that is what we have got. So from here, this is gonna be 0 into anything, 0 plus this, that's gonna be simply this, right? So here you see, so therefore f of a, from here what we're gonna have, f of a, if you find f of a, this implies f of a is equal to 1 by 2 pi I integration along c f of z by z minus, just let me write it properly, along c f of z by, just wait, z minus a dz. So this is what This is Cauchy's integral formula proved. So hope you have understood this and hope you enjoyed this video, and if you have enjoyed this video, please hit the thumbs up button and share with your friends. Stay connected and subscribe the channel if you are new to my channel. Also hit the bell icon so that you get notified when new video will be uploaded. So see you in the next video. Thank you for watching.